Good afternoon to all of you. So we are starting today with, we continue today with the material that we are covering in matrices, network matrices. At the same time, while we do that, we will introduce also some new concepts in terms of resonance circuits, series resonance circuits, parallel resonance circuits, and then quality factor. So the reason we am trying to combine the two new concepts with ones that we've covered the last few lectures is because this way we can become more familiar with the concepts that we are introducing in this class. Before we start with the material, presentation of the material, I wanted to say that yesterday we had, or Wednesday, we had our first problem solving session. I have uploaded the problems we solved and the solutions. So from my notes, unfortunately, the recording, for some reason, it stopped recording half an hour through the lecture. And when I tried to access this half hour, there was garbage there. So I don't know exactly what is happening. It's happening once in a while. Maybe there was an interruption that we did not see in Zoom, and that I've sent a note to IT to give me an idea. So I will try as long as I can access the file of the video of the lectures, either regular lectures or the problem solving sessions. I will put it up. But as I said, I had one problem with last Friday's recording, which also had the same kind of thing. And Wednesday's problem solving session recording that had the same thing. I don't know exactly why this is happening. I don't know whether it has to do with space available, because those files are several megabytes, like hundreds. And I don't know exactly what the problem was. But in any case, I will try to find out in case I'm doing something wrong. I just want to make sure that I do not do anything wrong. In any case, so with this note, also I would like to tell you that this evening, like later in the evening, I'm going to upload the homework for next week. And also I'm going to give you, as I said, until Sunday, not this Sunday, but a week from this Sunday at midnight, kind of like 11:50 something. So you have enough time to do it, but I will not extend it beyond that. So you didn't know. I was very lenient in the first few weeks until we all settle, but there are deadlines for a good reason. Deadlines are not there to violate them all the time, all right? Deadlines are there to be able to meet them. And I have to tell you, after you leave the university and you start working, their deadlines are really hard. For example, if you are to submit a proposal to receive money to do your work, whether it's an internal proposal to your company or a proposal to the government, they have 5 p.m. deadlines of given days. If you go there 5 minutes or 5 seconds after 5 p.m., you're done. So I don't want you to leave this class thinking that, okay, it's a deadline, it's just a wishful thinking. It's not a wishful thinking. I have been lenient on purpose because I know that the introduction to the class was kind of difficult and I wanted you to do well. But I have to tell you, if I make all of these extensions, there is not gonna be, for whatever reason, any extension. I mean, you can still submit it, but I can see how late it is. And I have the right to not give you grade if it's late. You also have the opportunity to make it up with make-up assignments that we will have 2 in this semester. But I just wanted to tell you, deadlines are there to be observed. The also other thing, I am ready this weekend to put forward for you, for the teams, the 3 possible receivers you can select from. And these receivers will come with some specs. Now, you're not gonna be graded on how well you meet the specs, but you're gonna be graded in this on the work that you do using the concepts that we learn to create that, and how well you know how your receiver performs. Again, using things that we will learn in this class. So I will give you specs which are reasonable for receivers, but again, if you develop a good receiver, I mean, you know, you take all of the steps, you develop a receiver which somehow is off, reasonably, I would say, not that the receiver does not necessarily work, but if it's off those specs, that will be fine. It's not like that we're trying to meet them exactly. I will explain that, and I will give you also material that is gonna help you in your thinking about what to select, and you will have, your teams will have to select this week. And then I would like, following week, I would like to see the teams to meet with me during office hours, because I do not have another way of getting to know you. And you know, it's nice in a class to know your students. So with that, I would like to conclude my announcements and see whether you have any comments or questions before I start with the lecture.
Yes, Professor.
Yes.
Homework 2 has no submission box.
It does not?
Yeah, we can see the PDF for the second homework, but like you can't click on it, open it up, and submit anything.
Okay, I will take care of this.
Okay, thank you.
For homework 2. All right, let me take care of this. So make a note here. Submission. For homework 2. All right, I will take care of this. Thank you for telling me. Any other comments?
Did you were talking about extending the deadline? Was that for homework 2 or would that be for homework 3?
You know, I can do it for homework 2, no problem. I'll make it at 11. I was planning to do it, you know, since it's open, I will make it Sunday at 11:58 p.m. Okay.
Okay.
All right, so now, any more? Any other questions? Okay. If we don't, then I will capture the screen as I do. Okay, and now I believe you see it. So what we are gonna do today, we'll start talking about resonance circuits. And resonance circuits are extremely important in high frequency circuit design. A lot of times you design them to resonate because you need that. A lot of times are just there. They have been in place because of all of the various components you put and then their interconnections, and create sometimes unwanted resonances, which of course is not a good idea to have an unwanted resonance, and we are going to talk about this. So we'll start with simple circuits, obviously, and we are going to work on those and then see exactly what happens. So let's take a circuit like this circuit here that has a load, and the load in this circuit is an RC circuit, is a resistor in series with a capacitor. So we have a circuit here. It's a matching network. We have designed it. Somebody gave us a load. There was a resistor and a capacitor. And I call that R sub L and C sub L. And then they gave us a source. And the source has an internal impedance. I simplified it here to be 50 ohms. And it's a source that has a voltage, Vs. And they said, okay, now we want you to create a matching network which is going to send the maximum power to the load. All right, so do you remember what we said about what kind of an impedance we want here to create the maximum power that goes to the load?
Needs to match the source impedance.
It needs to be the complex conjugate of the source. Remember that? Never forget the complex conjugate. Okay? Never forget the complex conjugate. So practically, what does your impedance do? It cancels if it's the complex conjugate of your load, of your source. So your source, let's assume your source here had a real part and an imaginary part, all right? Rs plus Jxs, which is possible because, I mean, in reality, it is that practically. And so here you design a matching network that creates here a Z in of A prime equals, let me do the ZS you suggested first of all. So that would make it Rs plus Jxs. And then this source here, V sub S, is going to see a load that is going to have 2 Rs to XS. All right. And so you can use that to find out that the maximum energy that goes into your network is not achieved when this is in place. It is only achieved when there is a complex conjugate here, which makes this one to be minus, and which is going to lead into this configuration. So always remember that, okay, for the complex conjugate, extremely important.
So the complex conjugate will make it so that no waves are reflected back to the source and all power is absorbed in the load element.
All the power is going to be absorbed, exactly.
Okay. Right.
Exactly. So now what, in this particular case, of course, Z sub S is real. So for real Z sub S, which is 50 ohms, we need to Z in at AA prime to be 50 ohms. Okay, so now there are, of course, I can use a transmission line model to achieve that, all right? I can use a transmission line alone or not. Do I need, if I use a transmission line, is that gonna be good enough by itself, or would I need something else in addition to it? we have a complex load at the end. We have a real part and we have an imaginary part in the load. The load is RL minus J1 over omega C. So if I have this load here, and since we've learned about transmission lines,
Professor,
yes,
some
excuse me?
somebody had a question. Why does the load change?
Let me see. Why does the load change to 2RS? The load that is seen by, well, because you have Z sub S, and let me see also, you have here the total. If you have a Z sub S in series with Z sub in, what is the load to V sub S? If they are identical, will be 2RS plus 2JXS. If they are complex conjugate, if Z in is the complex conjugate of the ZS, what happens when you sum a complex number and its complex conjugate? What happens to the imaginary parts?
It'll cancel out.
Yeah, that's why you have 2RS. Is that, was that the question? Okay. So here we have a complex load. All right, and I'm asking you now, since we've learned transmission lines, we still are working with them. Would you be able to just put a section of a transmission line to match it, like this?
You need a stub or open circuited stub?
Yes,
We use
you
a
need a
stub in general.
You need a stub in general, correct. Whether you're gonna use an open circuit or a short circuit depends so much on the geometry, and we're gonna come to this. But if I were to use a section of a line, at any point, I cannot avoid using a stub. Why is that? Because the section of the line will transfer the impedance here. And this, let's assume that this is an intermediate point, all right? C prime. Let's assume that A prime is somewhere here. All right? If I use a section of a line and I look at any point C prime, which is at a distance D from the load, the input impedance at that point, remember, is given by this. Is given, if this is Z naught, by Z naught, ZL plus J Z naught tangent beta D, Z naught plus J ZL tangent beta D. What kind of a number is this? Is it a real, is it an imaginary, or is it a complex for our case? What do you think? So I'm asking now.
What was your question again?
The question was, in our case, this is Isabel, all right? And if we were to use a section of a line to match it, then you said that we cannot do it without adding a stub. And I'm trying to explain why. Why is it that we have to add a stub? Because the impedance at any point of the line is gonna be given by this at a distance D from the load. And therefore, this formula, what kind of an impedance does it give? Does it give a real impedance only, an imaginary impedance only, or a complex impedance?
Complex.
Complex. And if it gives a complex impedance and we have to match this complex impedance, we have to make it real here, because that's what this condition told us. If we have to make it like you see this on the left, all right? So here is exactly, I'm talking about this one. All right, so you see that in my notes. If I have to make this impedance at Z in A prime, I have to change it from complex that it was at CC prime to real. Then the only way I can do it is if I add something that can only affect its imaginary part. All right. And then the only thing that we can create that it can only provide a imaginary load or a reactive load, as we call it. Imaginary that takes the name imaginary load means something different, obviously. So a reactive load, the only thing that creates a reactive load is a stub. And it can be open or short. Which one of the two you're gonna select depends a lot on the geometry of your transmission line. In some transmission lines, it's easy to make a short. In some other transmission lines, it is easier to make an open. So for example, if I use a microstrip is like this, and this is what we use in most circuits, then, and the microstrip on the surface looks like that, all right? A short means that I have to drill a hole here at the end and then connect the ground. And that's not, it's very difficult to do. I mean, if you could avoid it, you always avoid where punching through the wafer, unless you absolutely have to. There are cases where you do. But if you don't, in the microstrip, I'd rather do an open stub, all right? And a microstrip in 3 dimensions is gonna look like this, for example. All right, so it's gonna have a dielectric underneath it, here the conductor. And if this is a stub, on a microstrip line, I would rather have my stub be open at the end. Now, if I use a coplanar waveguide, which looks like something like that, and at some point we'll talk about this, and then I can come around like this, I bring the ground around it, this is my center line, and around it is the ground. The white area is like open, it's like the surface of the wafer. Then a short here is better. So in a coplanar waveguide, if I make my stub out of a coplanar waveguide, that a short is better. All right, then, and for a microstrip, an open is better. So which ones you choose depends on your geometry and general considerations about the layout of your circuit. All right. Now, in this case, since I need to use a,
It's 2 o'clock.
no matter what, I need to use a stub, I chose not to use a transmission line. All right, I will use an inductor. Let's assume that I am in low enough frequencies and I don't make this monolithic. So I can pick an inductor and put it on our board and connect it with the load. And then I have the source on the other end. So in this case, I chose for the given load that I have, which is the resistor and the capacitor, I chose to use as a matching circuit just a simple inductor. It's kind of ugly. Okay. And then I'm going to choose the value of this inductor so it cancels the reactive part of my load. Now, why did I also do that? Because RL, it has been given to us to be 50 ohms. Okay. If RL, so I can do this, let me write it down so you remember it. I can do this only an inductor L because R sub L is 50 ohms. So if I use the inductor to cancel, if I use this to cancel my capacitor, all right, to cancel the capacitor, then what is left is going to be exactly 50 ohms. And that's why it worked. What would happen if RL were to be 80 ohms? If RL, assume now that RL is 80 ohms, would I be able to use only lumped elements in the matching network? What do you think?
No.
No. What would I have to do?
You'd need to transform to the that impedance using a transmission line, like a quarter wavelength or something.
Exactly. After I put a stub. Or I need
Correct.
to put the transmission line first and then include a stub somewhere. Okay. Usually, if I have a load, also let's talk about layouts, because some things are so critical to how we lay out things. Let's assume that, that I have a load. Somebody tells me that your load is an antenna, all right? So I have an antenna here. It could be a microstrip antenna. It can look like this. If it's a microstrip antenna, it usually looks like that. And underneath has the ground, all right? So this is the microstrip, the top. Do you know what microstrip is? Is anyone who does not know what a microstrip is? Okay. If you have something like that, and that is RL plus JXL, then I would say that here, let me just close that. That here, I will have to be careful where I'm using the stub, because I cannot go, the input impedance, the input to the antenna is right here, which is right here. I cannot go and put a stub next to it because the stub is gonna look like this. So it's gonna impact my antenna. So what do? I don't do the stub there. I use a section of a line, first of all, here. All right, so I use a section of a line, which this is a microstrip line, so it's gonna work like a transmission line that is gonna have a distance D from the load. And then here, I'm gonna put, I will put the stub, and I will make sure that where I'm placing I'm finding D. So when I come here, this one is going to be Z in to be 50 plus J X in. And then here, I'm gonna place the stub. And I will use a open-end stub because it's microstrip. It's not gonna be so big, obviously, it's gonna be smaller. All right, and then I will continue after that. And at that point, this one is my matching network right there. Because here, with what I've done, I have a Z in, which is 50 ohms. Is that clear? So I'm introducing this to you now, so you're thinking that you have flexibility where to put your stub, to the left or to the right. I mean, if you have a transmission line and a stub, you can either put the stub next to the load and then the line, or the line next to the load and then the stub. And in this particular case, it does not make sense to put the stub next to the load because that has an antenna in there. There will be other cases where it may make sense because instead of an antenna, you may have just another section of a transmission line that is connecting you to another circuit, all right? So with this in mind, in that particular case, as you said, if my RL, R sub L, were not 50 ohms, then I would have to use, of course, a transmission line and a stub. But now that it's 50 ohms, my solution is simple. And the solution is this one. Okay, so now what do? I try to find the input impedance. Now that I have this network, all right? So I'm trying now going back to L as a matching circuit. It's a series L, obviously. It's an inductor connected in series. So my Z in this case, will be J omega L. I don't have a transmission line anywhere, all right? So I'm just doing circuit analysis, plus Z sub L. So it's going to be J omega L plus R sub L minus J 1 over omega C. Okay? Which means then that my Z in is going to be R sub L as a function of frequency, of course, plus, here I will write it as the following, plus J omega L 1 minus 1 over omega square LC. Now, this is kind of interesting because it shows that if I use this L, there is only one frequency, omega naught, where my Z input at AA prime equals to 50 ohms. So if I were to plot Z input as a function of frequency, it's not gonna be always 50 ohms, all right? So Z in as a function of frequency of omega is a function of frequency. It varies, it's not 50 everywhere. It is only 50, it is 50 only when omega equals omega naught, and omega naught is nothing else but 1 over square root of LC. Okay, why is that? That is true because if I go and place this relationship here, what I find is that indeed at omega equals omega naught, Z in equals R sub L, which is 50 ohms, plus J omega L. And here I have 1 minus omega naught over omega square, where now omega naught, omega, in this particular case, when omega is this, when omega is omega naught, all right, that very specific frequency, then Z in is 50 ohms. And when omega is different than omega naught, then Z in has a real 50 plus an imaginary part, which is different than 0. Okay? Any questions so far? All right. Because of this particular property in this configuration, we call this frequency omega naught, we call it the resonant frequency. And why do we call it the resonant frequency? We will see why we gave it that name. So first of all, we are going to look at, before I explain the term resonant, we are going to look at how Z in, I told you that is a function of omega, how Z in changes with frequency. And because Z in has this form that I gave you above, then we take, it's a complex number, we take its magnitude, which is nothing else but the square root of 50 squared plus omega I left an L squared here out. Okay. Which is going to be omega squared L squared, and then this one minus omega naught over omega squared, and that squared. All right, and in fact, you see that it's the same thing that I've shown to the left. Now, if you were to plot this, what you see is the following. Usually when I have functions like that and they are complex, I'm trying to find how they look at when omega is 0 and how they look when omega is infinite. So from this one, when omega is 0, both omega squared outside of the omega squared outside of this function and omega here, they both go to 0. And then we are going to see that Z in at omega, when omega goes to 0, is equal to, let me in fact show you how this, it's a very large obviously function, but it has both a real and an imaginary part. In any case, it's gonna look like a very large number, obviously. And then, as you see in this, and then as omega increases, this number goes smaller, and this number here becomes smaller, obviously. And then when it goes and becomes equal to, when omega naught becomes equal to omega, or omega becomes equal to omega naught, that reaches this value, which is nothing else for us but 50 ohms. And then as it goes away, it goes up again. All right, so we see that impedance goes like that. What happens right at this point? Let's think about this. At this point, we said from, which is here, this point.
Professor, what happens? I'm sorry, what happens to the J? Because I thought when we, maybe I'm wrong, but we squared the J, it would become, so at the absolute value or the magnitude of Z in omega, wouldn't it be 50 squared minus J?
So here, when to get this one, so let me show you. In complex numbers, Z magnitude square is Z in times Z in complex conjugate.
Thank you, ma'am.
Okay. And that's why it's a plus. Okay. So right at that point, going right here, at that frequency where omega is omega naught, what we find is that our circuit, which is up here, okay, so practically is looking like this one. I will write it, I will just lay it out horizontally. So it's gonna be our R sub L is our capacitor, and then is the inductor we put. I just changed their order. I can do that, all right? This is, these are reciprocal components. I can change them, their order. So it's gonna look like this. That's what we have. That's what we see from here. Do you agree? That's what we see. This is your Z in at AA prime. When this goes to 0, because that's what happens at omega equals omega naught. So your J omega L plus 1 over J omega C goes to 0. Then what happens is, like this circuit here, this part of the circuit, it's like, it is in a state where has no current that flows through it. But what that means is that in this state of resonance, the circuit is, what is happening in there is all of the charge, the energy that is stored in the capacitor transfers in the inductor, and then back from the inductor to the capacitor, and then back to the inductor. So practically there is a continuous exchange between electric and magnetic energy between the capacitor and the inductor. And that's why we call it, it resonates. It resonates because if there is if there are no losses in the capacitor or the inductor, over time, that exchange of energy can keep going forever. But obviously, in reality, that does not happen because any capacitor has capacitor losses through the metal, through the material, and inductor has inductor losses through the same reason. If it's if it has a ferro material in there because of that, or if it's only the coil because of the losses in the metal. So if you feed a circuit like this that has been designed with CNL at that particular frequency, so you send a wave into this circuit that is resonating. So let's assume that I take this circuit here at omega naught, and I send to this a continuous wave, which resonates, has a frequency of omega naught, so cosine omega naught t, that what is happening, which is very interesting, is that the capacitor first charges and then so starts storing electric energy. And then after it charges, it discharges, and then it moves all of the electric energy to the inductor, and then the other way around. All right, so for a long time, there is a transfer of energy between the capacitor and the inductor. So practically it resonates, and at some point you can think of cutting this, and that will still keep resonating, all right? Because the charges will be in the capacitor and they will move, they will become current for the inductor, and then the current will put more charges in the capacitor, and then that will keep going for a long time. In reality, if you do an experiment like this, you will find out that, of course, this back and forth between the energies will dampen over time, and it's going to go eventually to zero, both of them. So the circuit is going to just go into a zero state in terms of current and voltage. But that's a resonance circuit. When the energy in the inductor and the energy in the capacitor are equal. The energy in the inductor is magnetic. That's why I say WM. The energy in the capacitor is electric, WE. All right, that's why we call this the resonant frequency. Okay. Now, so when we, in this particular case, in the series resonance, if we find the magnitude of Zn, it shows that it creates a dip. Looks like that, more or less. All right, where this is the resonant frequency. And now we are taking the magnitude of this, and we are looking at what point from here it goes up, oops, to the point where it's like, this is going to be therefore RL squared. It's going to come up where it's going to be RL squared divided by 2. So right here, it has, well, times 2, I'm sorry, times 2 in this case, times 2. Okay, so we are looking at what point it goes from this value to that, which is twice this value here, twice this value here, and I will use a different color. This value up here is twice the value down at the peak. And then also there is another point here where that happens. There are two frequencies, one above, one below. And we call this, by definition, the bandwidth. So every resonator has a resonant frequency and has a bandwidth. And these are very important parameters to keep in mind when you design resonators, all right? So that is important. Why it is critical? Because in filters, we use resonators for filtering. So with that.
Professor,
yes.
in the figure on the left,
yes,
it has RL over the square root of 2.
Yes.
But on the figure on the right, we just have 2 times RL.
Yes.
Is that intentional to have RL over the square root of 2 on the left and 2 times RL squared on the right?
Yeah. So you see there, let me tell you why. Because if you take Z in to be equal to square root of 2 RL, how much is square root of 2? Is 1 over 0.707. All right, it's equivalent. Do you see that? Take the square root of 2 and then make an input, right? So I like to always do with a half, with 2, because it will mean something later to us when we start talking about power in dBs. All right. If you turn this value if you take, for example, why am I saying that now? We're gonna see it later, so it's a good time to introduce that. If I were to take the 20 logarithm of z in, and that at omega equals omega naught is gonna be the 20 logarithm of R sub L what happens when I go to 20 and I get 20 logarithm of z in, which is gonna be 20 logarithm of square root of 2 RL, and that is gonna give you 20 logarithm RL plus 3 dBs. 3 dBs means half in when you take it to the second power. So for example, that tells you that when you go 3 dBs away from your best, from the resonant frequency of this resonator, then that's where you define the two endpoints for the bandwidth. This is the low 3 dB frequency, omega 1, and this is omega 2. And omega 2 minus omega 1 is delta F, which is the bandwidth. All right, and usually we measure it in percentage. So it's gonna be, the bandwidth is gonna be, to be better in the definition, the bandwidth is gonna be delta F over F naught. All right, so in fact, let me, to be more accurate here, I will put here delta omega, and then usually it's gonna be either omega 2 minus omega 1 by omega naught, or it's gonna be F2 minus F1 over F naught, all right? It's the same thing. But I will use it in omega since we don't wanna go back and forth between omega and F. Or just since I introduced that there. Okay. So 3 dB, that's why I like it to go by 2, because it gives you 3 dB when you have the second power. Usually second power indicates power, and that's true. So in any case, the 3 dBs is what we always remember as the definition of the bandwidth. And that's why I did the other one.
Dr. Katehi?
Yes.
Did you mean to put the omega 2 minus omega 1 in the denominator? Because isn't the numerator the delta of them too? So wouldn't it just be
Yes.
1?
Thank you, thank you. This, in fact, I meant to do this. Omega naught and omega naught and F naught. That's what I meant to do. Thank you. And this is that. Okay. Here,
I think the class is already over.
Pardon me?
Dr. Katehi, I think the class has already ended.
Class is ended. Okay, thank you for telling me. What time is it?
It's 2:30.
2:30. Yes, thank you, thank you. All right, perfect.
5 minutes earlier.
With that, I have to tell you also, I'm gonna give you a quiz, which I'm gonna have until 9 p.m. today, 9 p.m. And the quiz, I'm gonna make it right now. With that, go to here, or rather here, and go to this is here. All right. Let me see.